All right, welcome back, everyone. Uh, we're going to jump right into what I think is the most fun aspect. So this is the basics of ferroelectricity and piezoelectricity. Um, this will probably stretch beyond just today's lecture into Thursdays because there's a lot to cover, and I get excited about things and want to go into more detail. If you have questions, please, as always, interrupt and jump in. Uh, Part of this may end up being a little dense. You can also tell me, just keep going. We'll look back at those things if you're bored with some of the details. Um, so yeah, just jump on chat and fill things in as we go. What I'm trying to do here is give you enough of the fundamentals and the understanding of the components of each of these phenomena so that we can follow this up with, okay, now how do I actually take advantage of that? How do I use ferroelectricity or piezoelectricity or these various other components of those for an application that is actually useful. So don't worry, we're going to get back to the useful parts towards the end of it. And hopefully it will all make sense when we get there. So we'll start off with a quick refresh of the crystallography aspect. We covered this earlier on. And this is really why we talked about the crystallography and the symmetry at the beginning. So we talked about point groups and pointed out that non-centrosymmetric point groups, the 20 of these are 20 of the 32 possible point groups are offer piezoelectricity as a phenomenon. So the other 12, 11, 12, depending on whether or not you count 4, 3, 2, point groups simply cannot ever be piezoelectric. It's just forbidden because anytime you squeeze on the crystal structure, you're going to get symmetric response, and that's not piezoelectricity. So we'll get into what that means in a little bit. And a reminder that of those piezoelectric ones, 10 of them are polar. These are the ones that are potentially ferroelectric. And so we'll come back to the crystallography in a second, but what does that piezoelectric effect actually mean? So when we lack a center of symmetry, that means that when we start with our unit cell, it's balanced. It's for the non-polar piezoelectric point groups, the unit cell, the crystal structure is such that it's perfectly balanced and there's no polarization built in at the beginning. But then you squeeze on it. And when you squeeze on it, the arrangement of the atoms means that the strain that develops gives you a separation in the net negative and positive when you sum up all of the ions. So if you squeeze on it, there's going to be at least one direction, sometimes it's more than one, where just the act of straining the material separates the positive and negative charge centers. So overall, you end up with a little bit more positive on one end, a little bit more negative on the other end. This is what non-centrosymmetry actually means, or what it translates into from an application standpoint. So you can also see just from Poisson's ratio that if you stretch the material in this direction, it actually compresses in this direction. So that you're used to seeing this in all sorts of materials. That's a normal response. We will get to what that means in terms of the piezoelectric response. So now suddenly it's gone from we're pulling it in one direction, we're getting a response in two, and then actually in 3 dimensions. So this is how we represent the piezoelectric response. This is a very simple 2-dimensional version of it, obviously. The other aspect is you can, when you do this straining, so when you stretch the material by separating those charges, you end up with an electric field that's built in. You can flip that around and apply an electric field. And by applying that electric field, pull. So for example, if you put a positive here and a negative on this side, you're going to pull the negative ions towards that positive externally applied electrode. And on this side, you're going to pull those positive ions. That's how we get strain out of a piezoelectric, is by applying an electric field, because you're just separating those charges at the unit cell first level. So that's one unit cell. You stack these up and they influence one another. And what you end up with is that polarization is a surface charge density. So even though we talk about this from the individual unit cell perspectives, and obviously we're going to extend this beyond 2 dimensions into 3 for a full solid, keep in mind that the polarization that develops, it's a surface charge issue because so that means that this surface and this surface are what matter. These in the middle end up balancing each other out. But it's this net negative that pulls this net positive over, which pulls this net negative. And so you end up having this charge separation throughout the volume of the material, but it's manifested and measured and used as a surface charge. So it's really just the surface charge density that we care about. That's this polarization. So the polarization is the part that we're interested in. That's measured in microcoulombs per square centimeter. That just basically means how many electrons do you have around per area. So that's a cartoon version of the piezoelectric response. How do we actually use it? So I've thrown together a bunch of examples here. So we've got everything from the spark generators. If you've got a gas grill at home where you push the button and it sparks and it lights the gas, that initial spark is from a piezoelectric. You can I like to buy the little hand versions of those from the grocery store where they have the big long wand on them. You take them apart and you can pull out the piezoelectric generator from inside of that and hand it out to students, and they can go around and shock each other with it. So that's one example where you're squeezing on the material and taking advantage of the charge separation that polarization, surface polarization that develops. Another option is within cell phones, there are a gazillion different examples of piezoelectrics. So we've got one diagram here showing how you have an acoustic resonance within an aluminum nitride thin film. That this is the way that signals are filtered in your cell phone. Pretty much all modern cell phones for the last decade have used aluminum nitride based FBAR, film bulk acoustic resonators, where the electromagnetic radiation comes in. That's how you communicate between the cell phone and the tower, and that gets converted between the electromagnetic RF into an acoustic signal. And the reason that works is because the acoustic waves are much smaller than the electromagnetic waves. And so you can, the reason that one of the big reasons that phones went from the ginormous, like candy bar brick phones of the Nokias from the late 90s and early 2000s into the Motorola Razr and everything since then was changing from electromagnetic filters into these acoustic filters, and saves you a heck of a lot of space. Other examples within cell phones are speakers and microphones, the accelerometers so that your phone knows when you're turning it around. These were initially deployed in the Wii and in the shock sensors for airbags and similar sorts of applications. Probably the type of application that has driven a lot of the development of early piezoelectrics is sonar, and its very close relative ultrasound. And now there's just unbelievable amounts of advances being made in medical ultrasound and beyond medical ultrasound, so non-destructive testing and other sorts of things. So these are applications where you're converting between electrical and mechanical energy, in this case for sensing. So you're sending out a signal and then using that same array of piezoelectrics to sense the response in return. So you're using the piezoelectric to vibrate something and then looking at those acoustic waves when they come back to you, and from that turning it into an image. And so the two examples here are just from ultrasound images, medical ultrasound images from some of the very early medical ultrasound where you could barely tell what the image was. It looks like a bean. And then even now, this image was taken, I think, from 10 years ago, where they've gotten even better beyond this. But just a lot of the advances are in the electronics, but actually the majority really come from the quality of the material that's used for that piezoelectric transduction. So going between electrical and mechanical energy. And my personal favorite is an application from the Army Research Lab from, again, about 10, 12 years ago, where they were using PCT thin films to make little wings for flying robots. And so, again, this is a case where you apply an electric field and you get a strain, and there's all sorts of fun things you can do with that. Right, so these are just examples of when you might want to take advantage of piezoelectrics. There are a lot of other possibilities as well. But in order to do that, you may have noticed that in some of those applications, some of them you're squeezing on the material. Sometimes you're applying a field. When you're applying a field, maybe you want strain laterally, maybe you want strain directly in plane. You're going to get all of them, and how you maximize what it is that you want comes down to understanding the directionality. And so this is where we get into some of the math and the matrix notation. I'll try not to get bogged down here, but it is important to be able to translate what kinds of properties you want, what kinds of sample configuration you want, what kinds of device configurations and layouts may be applicable for your application. So even if you've avoided the phrasing of tensors, you've run into them in some way. You're probably familiar with scalar. A scalar is just a single number. So density, temperature, these are examples of scalar properties. Vectors, you probably in physics learned about vectors using velocity as an example. So velocity includes a speed, which is a scalar, and a direction, which makes it a vector. So in order to have a full description of velocity, you have to have both the magnitude, which is the speed, and the direction, and you put those together, and that gives you velocity. Tensors are the same sort of concept. So in fact, a vector is just a second rank tensor. So this is just telling you now we can get more complicated with multiple dimensions. So now we're going to beyond that second rank tensor of a vector, first rank tensor would be the vector. That's just the pyroelectricity or velocity. So you've got one. Second rank is now we've got two dimensions that we have to worry about. So we have a magnitude that can change with directionality. So it's the example that's on here is thermal conductivity, where maybe it's really large along this direction of the crystal and a little bit smaller along that direction, these sorts of things. Piezoelectricity is fun because it ends up being a third rank tensor. So you're actually combining all of these together. You end up with the magnitude plus three different directions within the solid. So you can have different magnitudes of response in all three dimensions, and they can be positive or negative. So it's we're not going to go into the matrix math in gory detail, but I just want you to understand that this is where it's coming from. Lucky for you, we're not going to get into elasticity of a fourth rank tensor because it just gets even bigger, uglier matrices. The math is exactly the same. MATLAB can do it for you. You don't have to be able to write these all out on paper, but it's useful to know where they come from. And so you can also develop these representation surfaces of the various properties in multiple dimensions to visualize the magnitudes of these. So thermoconductivity, optical response, those are easy. They end up being ovals, so they're easy to see what's going on. The third rank tensors, piezoelectricity, you end up with multiple lobes and potentially positive and negative values in there as well. So they get a little bit harder to see, but you can still represent them in a three-dimensional shape. And the fourth rank ones get even more challenging to try and represent. And but it all comes out of the matrix math. So just remember that piezoelectricity is a third rank tensor. This is the reason that the symmetry of the crystal structure matters so much, is because this third rank of the tensor means that you end up canceling things out a heck of a lot. So to keep it nice and easy, what we're really doing, we're focusing on either the direct effect or the converse effect. These are exactly the same behavior. It just depends on whether you are applying a stress and getting a polarization, or you are applying an electric field and getting a strain. The D, I, J, K in the middle, those are the same values. So they're completely symmetric to one another. So you can either apply a stress and get a polarization, or you can apply a field and get a strain. It's the same piezoelectric property. We just use direct and converse to clarify which way that we're operating it. So are we squishing it and getting charge, or are we applying a field and getting strain? And so I pointed out earlier the fact that Poisson's ratio means that when we have a solid, if we stretch it in one direction, so the example here in the blue arrows, if we stretch it in one direction, it's going to shrink in the other two directions. You're used to seeing this with a rubber band, for example, or any sort of elastic behavior that 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 is commonly found, you're going to see this kind of behavior. The reason that it's important for piezoelectrics is that no matter what you do, if you're dealing with a solid, if you're squeezing on it, if you're applying a field, you're going to get a response in all three directions in some way. And so we will get later into some applications where we can maximize or minimize different directions and different responses if we know exactly how our sample is going to be aligned. And so that gives us another knob to turn when we start making composites out of these. One aspect that I wanted to bring up here is that the D33, and we'll get into in just a second where the nomenclature really comes from for these. The D33 refers to the amount of response in the same direction. So in that three directions. So this is the direction that we're applying a field. And so if we are applying a field in the three direction and we're measuring the strain in the three directions, so we'll call that in this case the blue one is vertical. If that's 3, then 1 and 2 are going to be, let's say that's 1 and that's 2. Those are going to be the other directions. Because the response, if we're applying a field in 3, the response in 1 and 2 is going to be roughly equivalent for a symmetric material. Then the D33 that we measure is actually going to be about twice the size of D31. So that this is Poisson's ratio all over again. I will hopefully clarify this as we go when we start getting into the matrix portions of it. But I wanted to point this one out ahead of time as to keep this in the back of your mind, that when we talk about the magnitudes of these, the reasons that they're related, all comes back to the fact that you're dealing with a solid and you're pulling it in one direction and it's going to shrink in the others. Or if you're squeezing it in one direction, it's going to expand in the others, these kinds of things. Another definitional aspect that I need to point out is this K-squared. And so the basis, the whole reason, the concept of piezoelectricity is really just converting between electrical energy and mechanical energy, or mechanical energy and electrical energy. You can go back and forth. Regardless of which direction you're operating, when you look at the ratio of the energy output over the energy input, that's represented as this coupling coefficient, which is K-squared. And so a lot of times you will see in spec sheets for materials or for the actual devices, you'll see the D33 value, you'll see a D31 value, you may see a D15 value. These are the kinds of things that are reported. And then K-squared is another one that is really just the efficiency of that conversion. So one important piece along those lines, if this K-squared value ends up being 1, then it's perfectly efficient at converting all of the mechanical energy that you put in becomes electrical energy. All of the electrical energy that you put in becomes mechanical energy. As with everything else, we never get 100% efficiency. So no material is ever going to have a K-squared that's exactly 1, but there are some that get pretty darn close to it. So as some examples, quartz, so crystalline quartz, SiO2, that's an ugly O, but crystalline quartz, the K-squared is going to be on the order of 1%. So not very efficient at converting between electrical and mechanical energy, but it works great for watches, for timekeeping, these kinds of things. Quartz is wonderful because it's actually very efficient from a loss perspective, even though it's not very efficient from a conversion perspective. And so I use that as an example because if we have this total amount of energy that we're putting in, even though quartz is only converting that amount, 1%, between electrical and mechanical energy, its loss is very, very low. So its loss may be significantly less than 1%. So that means that all of the rest of this, even though it's not being converted between electrical and mechanical energy, it's still staying as the other one, whatever the starting energy was. So it's not dissipated and lost forever. It's just not efficiently converted. For example, some other materials. So PZT, as we're going to get to later, the K-squareds may be on the order of 50%, if you're lucky. Usually it's a bit less than that. So maybe 35, 40, 50%, something like that. PMNPTs can be up in the 90%. In that case, they actually have a significantly larger loss than this one. So this may have a loss of maybe 1%, maybe 0.5%, something like that. So you'll actually lose a bit more energy, even when you're using when you're getting greater conversion because of the way that energy is dissipated. And so if you think way back to when we were talking about capacitors and in the real and the imaginary portion of the capacitance, that loss was dissipated in some sort of non-useful form of energy. So usually thermal energy. This is where the loss of that 10 delta goes. We have the same sort of scenario here. So the loss that I'm talking about, these values down here, that's the amount of energy that is dissipated into thermal energy or something along those lines. This K squared is referring to specifically to the conversion efficiency between electrical and mechanical. So that's hopefully not too terribly confusing, but it's also not necessarily transparent when you're looking at spec sheets or when you're buying these materials or making these materials or making the measurements. So I wanted to spend a little more time clarifying that a high K squared is referring to the conversion between electrical and mechanical. It is independent of the actual 10 delta, the amount of dissipated loss that is where the energy is just being lost and going into thermal. All right, so now we get into the matrix part. So if we're looking at the direct effect, these subscripts are the matrix directions. And so in this case, if we're talking about polarization along the I direction, then that's combined with the stress in J and K. And these are just arbitrary letters. You can really use whatever you want to. Convention is I, J, and K, elemental P. But really what they're referring to is relative to the polar direction of the crystallographic structure relative to the direction that you're applying the field. And so for I, J, and K, for example, those are going to be, these are all built around Cartesian coordinates, so they're going to be orthogonal. You can pick and choose which ones you want, and you can rotate the matrix according to that. But the reason we're going to stick with I, J, and K just as arbitrary directions that are normal to one another. So the polarization along these three different directions, what the subscripts mean? Yeah, sure. So you have three different directions. So this could be I, J, K, or it could be 1, 2, 3, and they're really so we use I, J, and K as the completely generic versions. They're just telling you the directions along these different Cartesian coordinates, and so which direction you pick varies with the application and varies with the crystal structure and varies with which direction you're applying the field. To start with, we're just going to say I is this arbitrary, it's sort of like X, Y, and Z if you were labeling the axes again. So this could be X, Y, and Z. They're all, as long as they are mutually perpendicular to one another, then you can really just label them any way you want to as a starting point. Hopefully that clarified a little bit. So the convention ends up being that the 3 direction is the one where you're applying a field. So that's what's represented over here in the D33. But to start with, just to go through the matrices, it's pretty arbitrary, really. All right, so we can represent this equation in matrix form by just saying that because the polarization is a first rank tensor, that just means that it's a vector. It says polarization just means you have a positive charge and a negative charge, and you've got some distance between them, distance at an angle, and then a magnitude. So that's it's just like velocity. It's just telling you I have an arrow, and that arrow tells me a magnitude and a direction. And so because it's a first rank tensor, it's just an arrow. You've got 3 different components. You can think of that as sort of X, Y, and Z. So how much of that polarization, if you have an arbitrary arrow sitting within these within these axes. I've got an arbitrary arrow there. I can represent that. There's going to be a 1 component, there's going to be a 2 component, and a 3 component. And so I can take any arrow that I want to, any vector that I want to within that Cartesian space and represent it by those 3 polarization values. The same sort of thing with stress, except now because stress is symmetric, as we can see on this end, when I strain something, I'm going to get a response in the alternate directions as well. So that means that I actually need 6 of them. And that ends up being, these are the direct components, and these 3 are shear. And so if you remember from when you learned any basic mechanics, if you stretch on something, just like this, the cube up in the top, then you're going to get strain that's directly responding to that. You can also shear it so that let's say you apply a force here and here, you end up with a trapezoid. I'm a really bad artist, I'm sorry. So by shearing it, you end up with a trapezoid, and those shear components are what are represented down here. And so this is sort of generic background of matrices. If that's confusing, I'm happy to point you towards some other resources that'll catch you up on it. Don't worry, it starts out really ugly, and then we get to simplify it as we go. The reason I'm pointing this out is because when you see something that says D31 or D33 or D15, I want you to be able to not necessarily draw the entire shape in your head, but recognize, oh, this one is I'm pulling in this direction, I'm stretching that direction. And this one is I'm pulling in this direction and it's responding sideways. And 5 is going to be one of the shear responses. So that's the level of understanding that I think is important to take away from this. But I want you to see where it comes from along the way. So what I've tried to represent here with these D matrices, the D, because this D is a coupling between a first rank tensor and a second rank tensor, that's why it ends up being a third rank, because it has all 3 components. It has the IJ and the K. And in order to represent that in a matrix, we need a 3 by 3 by 3 matrix, which is really a cube. So if this is basically a row, that one's a row, but it can be 2 by 3 or it could be 1 by 6. And the cube that we have in the middle, we've got 9 different components times 3. So we end up with 27 possible couplings of the 3 polarization components and the 6 shear components. That gives us 27 possible piezoelectric coefficients. So the easiest way to represent that is this 3 by 3 by 3 matrix, which is not exactly easy because that's a cube. It's hard to write down a cube on a 2-dimensional piece of paper. And so all of this was developed many, many years ago before we had MATLAB. And so people came up with shortcuts for how to represent these matrices. And so the first step is to recognize that of these 27, several of them are redundant. And so if we think about the response that we're going to get because the material is symmetric. So if we start with a square and we strain it, there is no arbitrary, there is no definite center point or starting point. So the strain is going to be symmetric. So we can define an arbitrary center such that the strain to the left equals the strain to the right. And so taking that same concept and expanding it means that we get to eliminate 9 of these coefficients right off the bat because they're symmetric. And then we further simplify things, and this is called Einstein notation. I'm assuming it was Albert. I don't actually know for sure. But where because we've now eliminated some of the redundancy, we can simplify even further and say that every time I see a 1, 1, I'm just going to shorten that to 1. And every time I see a 2, 2, I'm going to shorten that to a 2. 2, 3 becomes 4, 1, 3 becomes 5, and 1, 2 becomes 6. And so it seems like a weird combination to go, well, why is 2, 3 become 4, and 1, 3, that doesn't make any sense. But the easy way to remember it is that if you draw out the matrices here, you just go this way. So the diagonals are 1, 2, and 3, and then 4, 5, and 6. So that's again, just a convention. There's nothing first principles about this. It's just the way that everyone has agreed that this is the way that these will be represented. But it makes life a lot easier. And then because of that symmetry that we had, where actually the values that we end up with here end up being halved because they include the values from the others. So if we remember the example that I gave here, if I was straining it this direction, because it's symmetric, we're just going to talk about half of it. And so the values that are there end up being 1/2. So that'll come into play when we start combining these later on, but that's where it comes from. It's just the symmetry of when I strain this entire thing, I'm only talking about that one component of it, the half portion. All right, hopefully that hasn't lost anyone completely yet. But the nice thing about that is that using that convention means that we can take that 3 by 3 by 3, 27 member matrix and combine it into a 2-dimensional 3 by 6 matrix, which is a heck of a lot easier to write down. And it also means that we can get away with using just 2 subscripts instead of 3 every time we want to talk about the D coefficients. And so from that, we get these different D coefficients. So instead of D111, it's now D11, D222 becomes D22, etc. And so you are able to simplify things a lot and represent this. So we can do the same thing, whether it's the direct response in purple or the converse response in black. Again, this D11 is the exact same as that D11. It's just whether you're coupling stress and polarization or you're coupling field and strain. And so the D coefficients end up being completely identical. Please stop me if you need any further clarification on this. This is as complex as it gets. It now gets easier from here on out. So this is the gnarliest that we have to deal with. So if you followed so far, awesome. Now all we need to do is remember this is all just math at this point. This is the way that you don't have to know anything at all about the material at this point. This is just arbitrary matrix. This is how it would work out. But now we know that we can add in symmetry. So if we take that D matrix, so we've got a 3 by 6 matrix, which is really just representing the 3 by 3 by 3 matrix that we simplified earlier. If we had a crystal that had absolutely no symmetry at all, this is what it would look like. And we would have to have, or we could have, unique values for each one of these. So this would be, we've got 18 different possible coefficients for the piezoelectric response for an arbitrary crystal. However, because we know that from Neumann's principle that the symmetry of the unit cell is reflected in the symmetry of the properties, that means that if we have a unit cell that has any symmetry at all, if we have rotational symmetry, if we have mirror symmetry, if we have translational, and not translational because that would be a space group, but any sort of rotation around a point, then that simplifies this matrix, because if the value of the unit cell, if we rotate the unit cell 90 degrees and it's identical, that means that if we take the D coefficient and turn the matrix 90 degrees, that value has to be identical. And so when we do that multiple times, we end up with a whole bunch of these that just completely cancel out. That because of the symmetry of the unit cell, many of these will end up being 0, and others will be identical to each other. So as one example, this 4MM is a common tetragonal point group. All of these little dots are 0. The coefficients are 0 in those positions. So this would be D11. and this would be D22. Those are 0 for the 4 point group because they end up canceling out because of the symmetry of the crystal. So that simplifies things greatly. That means that we have a unique D33 down here, and these that are tied together mean that the values are quantitatively the same. So D31 in this case equals D32. They're the same value because of the symmetry of the crystal. And so that means that, oh, and this is another example of the shear component. Just trying to show, because this is much better than my poor artistry, showing that when you apply a field, then the strain that develops is what's represented by these coefficients. And so from that, it's just another example. Class 3-2, this is the one that is, so 4 one example of this would be tetragonal barium titanate. Sorry, tetragonal. This would be SiO2 quartz, is class 3-2. And so the key down here shows you that wherever these little dots are, those are 0. The solid lines are a non-zero value. When they're connected by a line, that means that they're the same. When it's a solid line with a hollow, or a solid dot with a hollow dot, that means that they're equal but opposite in sign, et cetera, et cetera. So all of those symmetry relationships for all the different point groups have already been calculated. They're really easy to find. The Nye book that I mentioned here has all of these tabulated, and that's a go-to resource for these kinds of things. You can find them also anywhere online because they're very useful across a bunch of different applications. But because of that, the nice thing is that we don't have to deal with this massive 27 component matrix all the time. Most of the materials that we care about are going to end up having some amount of symmetry that's going to reduce that. And so if for some reason you have an application design where you really need a D34 response, let's say that's something that you've come up with, you've got a clever design. If you only had a material that had a D34 response, you could look through these collections of point groups and say, well, I'm going to have a single crystal of such and such point group. Otherwise, that value is going to be 0. And if I try to make this clever design that I've made out of a material that has any higher symmetry than that, then I'm going to end up with a 0 for that coefficient. And so that's another way to look at these symmetry components. All right. So as a reminder, all of these things that we've been talking about so far from a symmetry perspective are for a single unit cell or for a single crystal. How many times do we use perfect single crystals in applications? Well, quartz is one example. We use single crystals of quartz for the piezoelectric response. We use single crystals of lithium niobate, lithium tantalate. PMMPT grown single crystals are fairly common. But we also want to be able to take advantage of ceramic processing techniques so we can make cheaper things out of powders, so that we can make more complex shapes out of powder, so we can make more complex chemistries. So what does this really mean if we're dealing with crystal, or if we're dealing with ceramics? So all of the relationships we talked about have been for single crystals. What does that mean for a polycrystalline ceramic? So what is the symmetry of a polycrystalline ceramic? If you start, each individual grain in that ceramic is going to have the symmetry or the lack of symmetry of its point group. But then you take millions or billions or trillions of these crystals and throw them together into a ceramic, they're overall going to be random, right? So if it's completely random, then all of those moduli vanish, and we end up with an infinity M point group for a polycrystalline ceramic. So that's, I've taken my powder, barium titanate, PZT, quartz, it doesn't matter what it is. I make the powder into a ceramic, it's random. I sinter it, it's still random. I no longer have any piezoelectric coefficients at all. But we know that we have polycrystalline ceramic piezoelectrics. So how do we get that? We break that symmetry by doing a process called poling. So if you apply an electric field, then you can pull this polycrystalline ceramic. And instead of having an infinity M symmetry, which basically means everything is completely random everywhere, by adding this polling process. So let's say you've got a pellet. Well, let me try that again. We've got a pellet, and now we apply an electric field. Now we're able to break that symmetry by imposing another low symmetry on top of it by applying this electric field. So that means that we no longer have, we still have infinity rotational symmetry around, and we still have a mirror plane, but we no longer have the infinity rotation in this direction. And that means that we can, we end up with a matrix that gives us, just like in 4MM, D31 equals D32. And then we have D33 is non-zero. And then we have this D15 equals D15 coefficients. And so this requires us to be able to change the symmetry of the material by applying a large enough electric field to actually get some rotation of some sort within the material. And that's where ferroelectricity comes in. So I guess before I leave this, keep in mind that any polycrystalline ceramic piezoelectric has to also be ferroelectric to be useful. Or you have to have another way of imparting crystallographic asymmetry to the material in order to get away from this problem right here. So let's say we start with quartz. It's piezoelectric in a single crystal form. We can use it as a piezoelectric, as a single crystal. If we were to fabricate a polycrystalline ceramic of quartz, which wouldn't happen because you'd end up going through a phase transition and it breaks, or you go high enough and melt it and turn it into glass. But let's say that we could form a polycrystalline version of quartz. Each individual grain will be piezoelectric, but they will all be randomly oriented. So you apply a strain and then the charge that develops all cancels out. Or you apply an electric field and the strain that develops all cancels out because you've got equal numbers of responses in every single possible direction, and they all zero. So that means that in order to use a polycrystalline ceramic as a piezoelectric, we have to be able to pull it. One option is for it to be ferroelectric. Another is to build in some sort of crystallographic texture. So in one of the early examples, I showed aluminum nitride based thin films. So aluminum nitride itself, until recently, was considered the prototype piezoelectric that is not ferroelectric. And in 2019, some colleagues in Germany showed that once you modify aluminum nitride with scandium nitride, you can actually get it to switch. But the coercive fields are enormous. So we're still nowhere near a ceramic aluminum nitride based piezoelectric. But the reason that we can use aluminum nitride based piezoelectric thin films in our resonators and cell phones is because when we grow the thin films, we can grow all of the grains pointing in the same direction. So that is essentially equivalent to poling the material. If you can grow it in a direction where that polar axis is all, or the piezoelectric axis is all aligned in the same direction, that's just as good as poling. But it's not always easy to get your samples to grow with all the same crystallographic texture. So if we have time later on, we'll get into other ways of texturing polycrystalline ceramics through templated grain growth and those kinds of techniques. But for right now, we're going to start with completely random polycrystalline ceramics, and then we're going to apply an electric field and get those to pull. And that requires ferroelectricity. So that means that we need to be able to change the crystallography of the sample a little bit by applying an electric field. And so we use the perovskite example. We'll call this barium titanate just as a starting point. The concepts are applicable across just about any other kind of ferroelectric as well, the vast majority of them at least. So we will, if this were barium titanate and we have this perovskite unit cell, at high temperatures, so for barium titanate, this would be above 125 C, the material is cubic. And when it's cubic, it has a point group of M3M. And so that's cubic, it's very high symmetry. And if we plot the free energy, Gibbs free energy, so it's a G, versus the displacement of this center ion. So we're going to be, what we're plotting on this chart over here is where this center ion sits within its unit cell as a function, and the free energy as a function of that displacement. So at high temperature, when we're cubic, then if we push, the ion really wants to be here. If we push it, so displace it in some way, that pushes the free energy up. So it requires energy to move this ion out of its center. And so if we try to displace it by pushing it to the side or up or down, it doesn't matter which dimension we're talking about at this point because it's symmetric. Then that requires energy, and then we let go of it, and the free energy is going to go back down to its lowest point, and that displacement is 0. So as we cool it down, this energy well is going to get fatter. And so as we lower the temperature, this energy well is going to get broader. And so it's easier, it takes less energy to displace this ion to the side or up and down. So the ion can move around more easily. If you remember back to the permittivity that we talked about, there was a peak in permittivity above the phase transition. So as the barium titanate was cooling down from cubic towards tetragonal, the permittivity went up, and that's because of this. That makes it easier. It takes less energy to displace the ion back and forth. Eventually, we get to a point where this the free energy wells that we were describing here break apart into two discrete wells. And so what that is representing is the fact that when this unit cell becomes tetragonal, so this is now tetragonal, so the C-axis is longer than the other two, the ion is really happy being some displacement offset from the center. And so this ion has shifted out of the center, and it's sitting either just above that center plane or just below that center plane. And once it's in one of those regions, you can still displace it a little bit to either side, but you let go and it's going to relax back to that same displacement. So it's not happy being directly in the center of the unit cell. If you manage to push it over to the center of the unit cell and then remove whatever force you're using, it's going to slide back to one of these displaced regions. So that's really just representing, hey, we have a tetragonal unit cell that is polar. That's all this is saying. What makes this ferroelectric is if the energy barrier represented by this this free energy between these two low points, if that energy barrier is something that I can apply an electric field and get the ion to hop over, if I can push that ion or pull that ion with an electric field from one of these energy wells into the other one, that means that I can change the polarization of this unit cell between pointing up and pointing down. And that being able to apply an electric field and change the crystallographic polarization, the direction of polarity of that unit cell, is the definition of ferroelectricity. So this is for, well, I mean, it's generic for any sort of ferroelectric, any normal ferroelectric. We're using barium titanate as an example. So using this cubic to tetragonal example, I mentioned before that this is, if we're looking at relative permittivity as a function of temperature, that in this high temperature form where it's cubic, as we decrease temperature towards the phase transition temperature, so this is the Curie temperature, where it transitions between cubic and tetragonal, that the relative permittivity increases because it gets easier to move those ions around a little bit. So specifically, we're focusing on that center ion, the titanium and barium titanate. But really, it's a collective response of all of the ions. So all of the positive ions, all the baryons and all the titaniums are shifting a little bit. All the oxygens are shifting a little bit. So pretending that it's just the titanium is overly simplistic, but it's a useful starting point. So you can, as long as you keep in mind that everything is moving together, you can think about it as a simplified version. It's just the titanium shifting. So if we look at the unit cell after it's turned into tetragonal, so this is the tetragonal side. Whoops. Crystallographically, this is the 100 direction. That's 10 or 010, and then 001 is vertical. So the 100 and 010, A and B, are identical to one another because it's tetragonal. The C-axis is along and it's different. So you'll notice that the relative permittivity, and again, I'm going to change this to ER because it's relative permittivity instead of dielectric constant because it's not constant. The relative permittivity is actually larger along the 100 direction than it is along the 001 direction. So why might that be? Once this, even though the polarization is along 001, so that that ion has shifted up in position or down, but it's shifted along the C-axis. But once it's already shifted, then it's harder to get that ion to stretch any further. And remember, relative permittivity is dP, whoops, it's dP dE. And so it's how much change in polarization can you get by adding a field. So the amount of total polarization is large along 001, but the additional polarization that you can get by applying an electric field, a small electric field, is relatively small there. So that's why the overall relative permittivity along 001 is relatively small. But once this ion is sitting up there in that above the plane of the oxygens, it's pretty easy to shift it back and forth. And so if we look at that in terms of the way that the hysteresis loop looks, if we are in the tetragonal stage, we can apply a small electric field and it can wiggle back and forth a little bit. If we apply a large enough field, then it switches all the way from, so for example, down to up. And that's why we'll get this hysteresis loop. And then we apply a large field in the other direction and it can switch down the other direction. In this, when we're in the cubic phase, so the cubic symmetry, we still get some nonlinearity in this region. And so it looks like a hysteresis loop like this, but it's really smeared out. And any hysteretic behavior that we're seeing here is really a field-induced, I hate to call it a phase transition because it's not really stable, but you are starting with a cube and applying electric field and stretching it just a little bit. And because the permittivity is so high, you're able to actually stretch the material enough that it locally becomes non-cubic. And so that's why we get this kind of hysteretic behavior just above the phase transition. Once we get high enough temperatures down here where it's more real cubic and stiffer, then we're no longer going to see that kind of response. The other aspect that we need to consider for the crystallography of these tetragonal unit cells is that when I was talking about the relative permittivity along each one of these directions, so if we've got this ion that's a little bit displaced along 001, so it's sitting right here, if we displace it a little bit, that takes a lot of energy. Along 100, it wants to be in the center relative to the XY plane. So even if it's shifted up along Z, it's still in the center in the other axes. Now I can apply a field and it doesn't take much energy to get a lot of displacement. So remember, the vertical direction here is the amount of free energy that's required, and the X and Y is the displacement. So that displacement is how much polarization I'm able to get there. So this is just a schematic showing you that what's happening from an energy perspective for that center ion along each one of these directions. So 0, 0, 1, it's already offset a lot. And so getting it to go any further from there takes more energy. Whereas along 1, 0, 0, it's relatively easy to get it to displace a lot. And that's why the permittivity along 1, 0, 0 is the highest. All right, so that's for a single unit cell. If we start to build these up, so even if we have a single crystal or a polycrystalline ceramic, each one of these unit cells is sitting next to another one next to it and next to it and next to it. And so if we look at how this unit cell is going to be influenced by the unit cell next to it and next to it, you can imagine because this material has a spontaneous polarization that's built into crystallography, that means that it already has a plus and a minus side. And so if you shove it next to another unit cell, that is going to basically influence the one next to it to also have that same polarization, because it's going to be a lower overall energy if they're the same, if they're coordinated with one another. But at some point, you build up enough of these, you have a whole bunch across your entire sample. If all of these are the same, then you end up with a macroscopic electric field. And so remember when we first started talking about this, separating positive and negative charges, which is the definition of polarization, brings with it an electric field. And if you have a large enough area of these, then it's going to encourage some of those to flip, to compensate, to accommodate that electric field. And so what you end up with is a region where you've got one portion that's positive and negative, and the other portion that's negative and positive. And so these end up being two different domains. Where it's still a single crystal. So for example, the oxygen sublattice is still completely coherent. If we look at these black grids across here and pretend that that's the oxygen sublattice, everything is still completely coherent. But in this region, whoops, I drew it the opposite. In this region, we've got it minus, plus, and then plus and minus. And so in between, we end up with this region that's sort of the transition from one polarity to another. And that's what I've tried to draw here by changing the magnitudes of the arrows. And that's where the displacement of that center ion is going to be just a little bit less and just a little bit less, and then it flips to the other direction. And so if everything is all pulled in one direction on this hysteresis loop, then it's going to be pulled up. If it's pulled in the other direction, it's going to be pulled down. And this process of applying a field and getting it to switch is ferroelectricity. So I've stolen a cartoon from David Scrimger, former colleague at Sandia, that put together this animation for his PhD thesis 100 years ago or so for lithium tantalate, showing how the displacements of the ions look as you're applying the electric field and changing the polarization. And so while this is for lithium tantalate, the same concept applies for barium titanate and PZT and all the others that we're going to be discussing. And so again, this is a simplified version for tetragonal, where the polarization axis is directly along the 0, 0, 1, along that C-axis of the unit cell. But what happens is now we can apply an electric field, and essentially, if we're applying a field that biases this domain, so we're enhancing the polarization of that domain, then we're going to essentially shift this domain wall to the right, and if we encourage the polarization domains that we're pointing up, then the way that those domains grow is by this wall shifting just a little bit and essentially consuming the domains that are of the opposite polarity. So what does that look like when we go through this hysteresis loop? If we're all pulled up, then essentially the titanium ion is sitting above. When it's all pulled down, the titanium ion is sitting just below the plane, and that defines the hysteresis loop as we go through that process. And so now we expand that beyond just the individual unit cells, and we look at what it looks like in a polycrystalline ceramic. And you may look at this and say, man, that's a mess. I look at it and say, that's a beautiful domain structure. This is from the Jaffe cookbook back in 71. The same kinds of samples are all over the place now. So what we're seeing here, so there's a few pores and second phases that are in there, but the part that really want to point out are all of these herringbone type domain structures. And so you've got very fine structures and then large domains as well. And so what this is representing, and remember, each one of these grains is completely randomly oriented relative to all of the others. But when we start in the cubic state at high temperature, so we centered this way above 125 degrees C, then we cool it to room temperature. It goes from cubic to tetragonal. And so if you think about this unit cell as it's going from cubic to tetragonal, there's not only the charges that are developed that we have to deal with as represented down here, but there's also strain associated with this increase in the 001 direction and decrease in the 100 and 010 directions. And so the combination of that strain accommodation and charge accommodation ends up creating these complex domain structures where within a single grain like this, you're going to have some regions that are pointing in one direction and some regions that are pointing 90 degrees to that. And then within each of those, you're also going to have let's see, I drew this backwards. So this one, the herringbone is that way. So we've got 180 degree domain walls that are charge compensating. And then this one is 90 degrees to that one. But then we also have positive and negative 180 degree domain walls within that. And so you combine all of these and you end up with a really messy looking overall picture where each individual grain is randomly oriented. And then within each grain, we also have these domain regions where even though the oxygen sublattice is completely coherent, we've got the cations that are displaced just a little bit in each direction to minimize the overall total free energy of the system. So the fun thing is, because this is ferroelectric, once we apply an electric field, we can get those domain walls to move and get the overall polarization of the sample to become non-zero, not averaged out to be zero everywhere. And so that hysteresis loop that we were just looking at on the previous example, when this is some of the early work from, I think these were actually from Mertz that Jaffe, Cook, and Jaffe republished. When you look at the polarization hysteresis loops for a single crystal, it's a very sharp transition because all of the crystals or all of the unit cells are completely aligned because it is a single crystal. And you get to a large enough electric field and everything switches at once. And then as you keep increasing that field, you've basically saturated it. And you're stretching those bonds a little bit, but the amount of polarization that you're able to get after you've fully saturated that material is relatively small. And then we flip the polarity of the electric field around and go back the other direction and get to what is known as the coercive field. So that's how much field do we actually have to apply to get it to switch. And then the material switches polarization and flips the crystallographic direction of those dipoles. And then once it's all pulled, then the continued field, it's saturated and doesn't stretch a heck of a lot more. Look at the same kind of hysteresis for a polycrystalline ceramic. So now instead of having a single crystal with all the unit cells perfectly aligned, now we've got that random polycrystal like the picture I just showed you on the last slide. And everything is completely randomly oriented. And so some of those domains are going to switch relatively easy. So if we start, it's going to be zero when we first start off. Some of those domains are going to switch relatively easily, and others are going to take more and more and more and more field before they eventually switch. So we were able to saturate, but it's at a much lower overall value than in a single crystal. And that's because if you've got a grain where that C-axis is oriented this direction and you apply a field here, the best you're ever going to get is off axis by this amount. You can't really change where all of the lattice is located. You can only move the individual cations a little bit within the symmetry of the crystal. And so because of that, the maximum polarization that you're ever going to get out of a single crystal is much larger than the maximum polarization you can get out of a polycrystalline ceramic, just because of the cosines of the angles of the polarization of the individual grains. So, for example, if you have a grain here, you can have randomly oriented grains all over the place. If you apply an electric field in this direction, that one can't rotate any further. This one can flip. Here we go. And this one might rotate 90 degrees so that it's aligned in that direction. This one we can probably flip 180 degrees. And so the overall maximum is not perfect, but it increases over the completely random beginning. So you'll also notice on here that this coercive field, so the amount of field that is required. So the coercive field is how much field does it take to actually get the material to switch in the first place. The coercive field is much larger for the ceramic. And that's because there's strain associated with getting those the dipoles to reorient, and the cosine of that angle of alignment with the electric field. So let's say the dipole is pointed in this direction. If we apply an electric field here, the dipole only sees a component of that electric field. So geometry comes back to haunt us yet again. All right, so to give you a more visual schematic of this instead of my scribbling, I tried to represent this in terms of arrows representing the polarization directions of various domains. And so this is just a generic hysteresis loop. So we've got electric field E, polarization P. This PS is a spontaneous polarization. PR is remanent. And so you'll notice that's kind of a funny spelling. That is the IEEE convention, the standard spelling for remaining polarization or remaining magnetization after having removed a field. In colloquial English, it's remnant with no A. According to IEEE, we have to add the A in there when we're talking about polarization or magnetization, and so it becomes remanent. I didn't get to choose it, but it's an easy way to tell whether someone is familiar with the field or not if they use the English version or the IEEE version. So if we start off a completely random sample, it's been sintered and densified and then cooled, and it went through a phase transition, just like we talked about with barium titanate. Then you're going to end up with grains that are completely randomly oriented relative to one another. And within those grains, you will have formed a bunch of domains that minimize the overall free energy of the system. And they do that by minimizing the macroscopic electric field and by minimizing the macroscopic strain. And so what that means is you end up with this collection of domain structures within each grain. And then there's going to be, you'll notice there's some coordination across grain boundaries, and exactly how much of that applies depends upon the nature of the grain boundary and the magnitude of the spontaneous polarization and all sorts of factors. But it is fun to see domains that actually cross grain boundaries, because when you get to the end of a domain at a grain boundary, there's still going to be a surface charge there, and that surface charge will influence the domains on the other side of the boundary. So the point is, if we got the double circles are representing arrows pointing out of the plane at us, the X's are representing arrows that are pointing into the plane away from us, and the others are kind of sort of meant to be in other directions. As we increase an electric field, so we're increasing the electric field in this direction, the polarization, the sample is going to respond by polarizing. So you apply an electric field, the positive ions are going to go one way and the negative ones are going to go the other way. That's what polarization is. The domains that are most favorably aligned with the direction of the field that you're applying are the ones that are going to respond first. So it's low strain to switch 180-degree domain wall because there's really not a heck of a lot of strain between this sort of a scenario. If you've got the long axis, the C-axis of your tetragonal, and we're going to use tetragonal as the example, but you can extend this to any other low symmetry as well. If the long axis is pointing in the same direction, simply moving the ion from one direction to the other doesn't really strain anything. So these 180-degree domain walls are the first to switch because they're the lowest energy required to switch. So as we continue to increase the field, we will gradually get 90-degree switching as well. And so that means that these domains are going to switch to pointing up. These domains are going to switch to pointing up. And so we end up with everything saturated, so pointing as close to the direction of the applied field as we can get, according to the way that the overall lattice is aligned for that grain. Then we've fully saturated everything, and now we want to release the field. So we're removing the field, and we're going to go back the other direction. And because we've relaxed the field, we've relaxed the electric field. Some of to minimize the overall surface energy, the overall energy, and the strain that has developed by switching those 90-degree domain walls. Some of these domains are actually going to switch back. So this one used to be pointed in that direction, and now it's gone through a 90-degree switch. And with that, it also developed 180-degree domain walls. And so we end up with this polydomain response after removing the field. And that's why there's a finite difference between this saturated polarization. So the PS is saturated. So if we extrapolate this value back to the axis, that's PS. And it's never going to be exactly the same as PR because there's always going to be some finite amount of back switching, as it's called. And that's driven by the strain and the the polarization that's built in there, wanting to switch things back. As we now apply an electric field in the opposite direction, so let's say we applied this polarity here. Now we've removed that and it's at 0. Now we want to apply an electric field in the opposite direction. We continue around this loop, saturate at the other end, and the magnitudes of these, all else equal, the magnitude should be equal and opposite in value, and then the coercive fields should be equal and opposite. There are reasons that you can end up with some asymmetry in that, and we'll get to those later on as we go. But by default, if we're imagining a perfect defect-free material, those are going to be the same. So this is sort of a cartoon schematic of what's happening as you go through this polarization. Now you'll notice we never, even once we're here, when we apply a positive bias again, remove the negative bias and then apply a positive bias, we never get back to this completely random starting point. So we're just switching between pulled in one direction and pulled in the other direction. And when we're sitting at 0 field, we're going to have some version of this sort of mixed polarity where it's mostly pulled in one direction, but not completely, as represented by that remnant polarization. So we're by changing the polarity of the applied field, we're basically able to switch between this remnant state, positive remnant state, or negative remnant state. We never get back to that completely random starting point because what's happening here locally is we've got that free energy barrier where we have to, every time we switch, we have to hop the ions over that barrier. And when there's enough of them, there's a barrier that barrier represents this remnants where things are just going to be perfectly happy sitting on this side versus that side because the positive remnants and the negative remnants are equally likely. And that's what gives us our time-dependent, history-dependent response is that we can push everything into one of those energy barriers and just let it hang out there. So if we do, for some reason, want to end up back at this completely random state, the best way to do that is just go through the phase transition again. So if we heat the material up into its centrosymmetric prototype structure, so in this example, we'll go take that barium titanate, heat it up to 150 C or 200 C or 500 C. We get high enough above the Curie point that it's definitely cubic and it's relaxed, and then cool it back down again. We will see this completely random behavior again. Again, there's modifications to that with defects, and we'll get into those a bit as we go. But as a starting point, this is what a ferroelectric hysteresis response looks like. And so why does this matter? Well, the very simple reason is this remanence, you've got two completely identical inverted states. You can think of that as, for example, the ones and zeros of computer memory. There are ferroelectric memories that are based on that. You can also, this is how we break the symmetry of the polycrystalline ceramic to create a bulk ceramic piezoelectric. So in this case, even though each individual unit cell is non-centrosymmetric, it's polar, it's piezoelectric, by the time we add up the contributions from all of those domains and all of those grains, it equals out to zero because of the equivalent macroscopic infinity M symmetry. But once we have landed in one of these remnant polarization states, now we no longer have infinity M symmetry. We have infinity M, which gives us that same matrix as the 4MM. So we are able to have a D33, a D31, and a D15. And those are non-zero values of piezoelectric response, even in this completely originally random polycrystalline ceramic. So that's how we're able to actually make ceramic piezoelectrics, is because of this ferroelectric response. So I'm going to go into a little bit of information about the dynamics of how this happens. So I want you to think about how that process of actually going around this hysteresis loop occurs, and give you a couple of more tools that may be helpful if you're working in ferroelectrics or piezoelectrics. And then we'll jump to some more applications and some specific examples of PZT and others after that. But let's start with how does this actually work? So this is an observation from Walter Merz that has turned into what's known as Merz's law. So if you start off with he was doing this initially with barium titanate single crystals that he'd grown in his lab. But it's been extended to all sorts of other materials as well along the way. If we start off with a material that is pulled in this direction and we apply an electric field that's the same, then we basically have a capacitor, we charge the capacitor and discharge it, and that's the end of the story. If we start off with this same material, but now it's pulled in the same direction, but we apply a field in the opposite direction and actually get the material to switch polarization so that it goes from being pulled up to pulled down. That process of switching, we first charge the capacitor, but then all of this charge is associated with flipping the polarization of that material from pulled up to pulled down. And that charge is essentially what's represented by that hysteresis loop. But you'll notice this is drawn as charge on the left as a function of time. And so it doesn't happen immediately. So these ions take time to actually shift from one position to another. And it can be pretty darn fast, but it's still not instantaneous. And so looking at how fast this switching process occurs, Merz plotted this up and showed that you get a relatively linear response. So the higher once you get to a coercive field, once you push hard enough to get that switching to start, you can make it go faster and faster and faster by applying a larger and larger electric field. And it's a relatively linear response until you start to saturate and get to the point where you would be pushing the domain walls so fast that they're going at the speed of sound within the material. And the reason that that speed of sound, the acoustic velocity, is essentially a speed limit for domain wall motion is because those domain walls are essentially carried on phonons. So it's the atomic vibrations that allow those domain walls to move in the first place, and you can't go faster than the natural acoustic phonon vibration within the material. And so most of the experiments are done way down here at much lower domain wall velocities, but there's been a handful of work, theoretical and experimental, that have verified this over and over again for a variety of different chemistries and geometries and things. And so this relationship between how fast the domain walls move and how hard you push them with the field is known as Marx's law. It is really just another representation of the same nucleation and growth processes that you've seen in any other nucleation and growth sort of behavior. It could be crystallization from a glass ceramic. It could be crystallization of a snowflake. It could be growth of a water droplet in a cloud. Anytime you're getting nucleation and growth, you use the same JMAK kinetics to describe this. And so you've got from an energy perspective, it's basically a balance between the cost of creating a new surface and the benefit of gaining volume of a lower free energy phase or lower free energy polarization or lower free energy, whatever it happens to be. And so you're balancing this R squared term with an R cubed term, and that gives you a critical radius that says if you have enough energy to create a nucleus larger than this critical radius, then you're going to end up saving energy and things will grow. But if you don't get enough energy, if you don't create a large enough radius, then it's going to shrink back and go back to its lower state. And so using this same kind of nucleation and growth processes to describe ferroelectric domain wall growth happens all the time. The part that I want to point out here is that the cost of this surface is because when you have these domains that are pointing at each other, that ends up being a very large charge density. So if you've got the polarizations where all of the positive charges are in the same region, that's an expensive surface. That's what is referred to here as the cost of that surface energy. And so because of that, in a single crystal or within a given grain, the growth of these domains along the direction of the applied field is going to be much faster. So 10 times, 100 times, sometimes 1,000 times faster than the lateral growth, because the cost of having these head-to-head domains or tail-to-tail domains is much higher than having a side-by-side domain wall. And so these kinds of domain walls are called charged domain walls because of this charge, and they're much more expensive than these less charged domain walls. And so that drives the different kinetics that you see during this grain growth process, this nucleation and growth domain growth process. So these are all within individual grains, and then you expand it out to the full ceramic. So you can actually make measurements of this ferroelectric switching and compare that back to the nucleation and growth kinetic equations that have been developed for everything else. Ishibashi was the one that extended the Kolmogorov and Avrami JMAK. He extended that to ferroelectric domain growth and switching, and showed that when you represent the equation in this way, you can actually tell how the domains are growing physically based on the exponent. So if you start with pre-existing domain nuclei, if you start with nuclei, then the dimensionality of growth is represented by that exponent. So if it's growing in one dimension, then you end up with so it's like a single wall moving, then that exponent is 1. If it's two-dimensional growth, So it's growing laterally, then it's 2. And if you're actually getting volumetric growth, then that exponent is 3. And of course, if you have an exponent in between there, then you end up with some mixture of all of these. And so there's also a version called nucleation limited switching that was developed by Tagantsev that says, you know what, because of the cost of those head-to-head domain walls, it's actually lower energy in some systems to just nucleate a new domain and get it to grow rather than having the domains grow laterally. So nucleation limited switching is what happens when it's the energy barrier to create a new nucleus is lower than the energy cost of growing laterally. And so you just nucleate, and eventually switch the entire sample that way. And so this is actually seen in a lot of ferroelectric thin films in particular, where it's pretty easy to start a nucleus and get it to grow, but it's the cost of expanding the domain walls laterally is expensive. And so from this, you can actually look at what happens if you're getting nucleation if you start off with all of your nuclei at the beginning and then there's no additional nucleation, or if there's continuous nucleation happening as you go, or even this Jacobs version where you start with a bunch of nuclei and then you're adding more, but the rate of adding more decreases. Strangely enough, when people, so I'm using an example from Brian Huey's group here, when people actually measure these kinds of things using scanning probe methods, what we really see is a distribution of nucleation time. So it doesn't match any of these nice, simple examples. But people, for the most part, still use the same basic equation to describe what's going on. However, there are some scenarios where you actually get a lot of growth of domains even before you get, while you're increasing the nucleation rate. So everything from here up was already covered in classic models. A former postdoc of mine who's now research faculty developed this model for what happens when you've got growth happening even before the peak nucleation rate. And the reason that matters is when you've got systems like the new wurtzite nitrides that we'll talk about later on, when you've got a massive barrier to nucleation and a really strong driving force for growth, that's when those extensions so it's basically breaking the assumptions of the original KEI model, but it still matches all the math of those, just with a little bit different boundary conditions. So that's how the switching process happens. We're going to get into more about what that means and how we can make ferroelectric switching happen easier or harder, depending on what application we want. And then we're going to translate that to the kind of piezoelectric response that we get out of these materials as we go in subsequent lectures. So we should be able to wrap up the piezoelectric stuff, the basics on Thursday, and then get into some more details on PZT and other applications or other materials. So thanks. Not as many questions in the chat today. Hopefully I didn't just bore you to tears with matrix aspects, but if you have any questions moving forward, as always, shoot me an email or put something in the chat. Thanks, everyone.